Okay. Now the errors that we have computed so far, okay, all of these are the classic error measures. And these error measures will always go down as you increase dimensionality. As you put more variables in, these error measures will always go down. Yeah. So this is not a very good measure when you're trying to compare two different models of different sizes. If it is the same size, then okay. So when you bring in a new variable, okay, so there must be a cost to that, okay, when you compare against the benefit of the reduction in SSC or any of the other measures for that matter. But there's always going to be a benefit. Sometimes the benefit is really large and good. Sometimes it is minuscule, not worth it, right? So there must be a comparison, or there must be a trade-off between the cost of adding complexity to the model by bringing in one more variable. You're making the model bigger, okay, and all the attendant problems that come with it. So that's your cost. And you can't ignore that cost, because if you only look at the reduction in SSC, you're only looking at half the picture that says, okay, you're going to gain something, but there is a cost involved. So how do you adjust that? So that's what these three things okay, they do for us. Okay. Final prediction error. Okay. Final prediction error is that. So this is somewhat like the adjusted R squared. So remember adjusted R squared in regression? So it's something like that. It assesses a cost to the fact that you're increasing the model size. So if you did this, then you get the final prediction error. So n plus p, so these two, add the two, and divide by n, right? And then you multiply that factor by, so n plus p divided by n, all right, and then you multiply that factor by MSE. So that is your final prediction error. So final prediction error is mean square error, okay, adjusted for the fact that we have p number of predictors. Okay. So you assess the cost for number of predictor variables. So it's slightly higher than mean square error. Okay. And AIC is a key information criterion. Okay. So that again does the same thing in a slightly different way, and once again the way in which these two, and then the Schwartz Bayesian criterion, I think that's what Schwartz Bayesian criterion, oh there it is, that also does the same thing like the Akaike information. So this is n natural log of SSC over n plus 2 times p. You can see these are not calculated for, the final prediction error is not calculated for validation set, because we are not predicting anything in validation. Validation set, there is no p involved in validation set. Okay. So n times ln of SSE over n, right? C7, okay, n times ln of SSE over n plus 2 times P. So there, that's the number right there. Schwartz is slightly calculated slightly differently. So the first term is the same, second term is P times ln of P. So what I'm going to do, just edit the cell and copy that and change that part alone. P times ln of n. Alright, so that's your Schwartz Bayesian criterion. Okay, so these numbers, smaller the number, the better it is for the purpose of comparing different models. Again, these three measures, okay, give you errors adjusted for the cost of bringing in more predictors into the equation. Finally, for absolute error measures, okay, so you have maximum absolute error and have it. Oh, I think it's there somewhere. I don't know, but you know how to do this, right? So it's you have to compute absolute value of the residual. All right. So you have absolute value of the residual and then compute the, for maximum, use max and well, it's no big deal. Average and you do the same thing for validation set, and the absolute value of the residuals, okay, then you do the average.